This is the QUIC protocol, and my name is Chris Lee. So QUIC is a transport layer protocol that was standardized by the Internet Engineering Task Force with RFC 9000, and it was designed to address numerous issues with the traditional TCP and TLS connections. QUIC runs over UDP, and it integrates TLS 1.3 to support traffic encryption. It is the foundation for HTTP3, and additionally, its implementation returns reduced latency with respect to connection establishment and efficient loss recovery by way of multiple HTTP streams multiplexed over a single connection. In terms of connection establishment, on the left side here, we have a traditional TCP handshake and TLS handshake as well. So we know that TCP uses a three-way handshake. This constitutes one round trip already. And after this handshake is completed, we still don't have traffic encryption implemented. So we need to call on TLS, and then TLS conducts its own three-way handshake. QUIC has integrated TLS here. So you can see we've already saved one round trip just off the bat already. And here we have an initial packet, and within that we're going to have a frame, a crypto frame that's going to have the client hello. And this is going to be used to establish key exchange and cryptographic parameters. The server will respond with an initial packet, and in that initial packet it will have another crypto frame, and it will contain the server certificate. This will have the server's public key on it, and we'll be able to use that to encrypt our traffic moving forward. So following the completion of this handshake, we're already supporting traffic encryption. So we need QUIC to address issues with TCP, such as high latency, head-of-line blocking, connection breaks on IP change, and slow protocol development and evolution. Slow protocol development refers to TCP because it's developed in the networking stack of the kernel. Any changes to TCP are going to require a full operating system update. Head-of-line blocking sort of refers to the way that TCP streams data, so it's an ordered stream. So if the segment at the front or a packet at the front of the first segment is having an issue and needs to be retransmitted, that's going to cause a delay in subsequent segments, even if the subsequent segment's delivery location is available. Connection breaks on IP change is sort of referring to, say we had a TCP connection on a mobile phone and the phone was on Wi-Fi, and then we walked out of range, or we disconnected from Wi-Fi and we changed to a cellular network. The change of an IP address or the change of a port number would drop our connection. There are a number of applications already using QUIC. So HTTP3, we see that quite a bit. That's the foundation. Video streaming, so YouTube, cloud services such as Google Cloud, and then the major browsers such as Chrome, Firefox, and Edge. For our functionalities, we have reliable data transfer. So this is our ACK frames. We know ACK frames, we've seen them with TCP before, and the idea here is very similar. So we're going to confirm packets that have been sent. So we're confirming to the sender that we've received their packets. Lost packets in this instance now need to be retransmitted with an entirely new packet and the next sequence number. So you cannot retransmit a numbered packet. This is good because it creates a clear distinction between the receipt of an original packet or a retransmitted packet. We have multiplex streams, and the idea here is we have multiple independent streams in a single connection. Every stream carries separate data, so we're not getting the head-of-line blocking that we were getting with TCP before. If there's an issue with one, it doesn't cause an issue with another one. Flow control. We have two types of frames. We have max data and max stream data. This is going to limit the maximum permissible data that can be sent per stream and for the total connection session. Congestion control, we can adjust our sending rates. Usually we'll detect congestion with RTTT changes for connection migration. And this is what we spoke about earlier with the idea of changing from wireless to cellular. We can survive IP changes and port IDs because now we're using a connection ID. And a connection ID is established during the initial client hello and server hello. So the client will decide the server's connection ID number, that'll be the destination ID number, and the server will decide the client's one, which will be the source, I guess, if we're looking at it from our point of view. And then the combination of those two numbers is the connection ID for the session. With encryption, we have the integrated mandatory TLS, and that's going to give us our confidentiality, integrity, and availability. For our frame formats, every packet sent encapsulates the sequence of frames. These frames include a frame type field and type dependent data. There's about 20 of them. I'm not going to go through all of them. One that we see quite often is padding, and this is sort of a protection against traffic analysis. So we're going to be taking smaller sized packets, and we're going to be filling them with just, meaningless padding just to bring the size of that packet up so that it's harder to figure out what's what. Crypto is another important one. This is used during the initial handshake. and we're going to be transmitting cryptographic handshake messages. We have the max data and max stream data frames that we covered on the last slide. For our advantages and our disadvantages, we have low latency, no head of line blocking, integrated encryption, connection migration, and improved performance for web apps. So say we're loading a website, and we will be able to simultaneously load the images and the videos on that website. In terms of our disadvantages, we have UDP blocking. So certain networks and firewalls are going to be configured to restrict UDP traffic, and QUIC is built on top of UDP, so that can cause an issue there. Monitoring and analysis, both genuinely and maliciously, is significantly more challenging because QUIC encrypts more data than TCP does. So we're encrypting headers and things like that. And deployment complexity, which is, that's a bit of a reach, but it's still there anyway. QUIC security versus the traditional TCP TLS. So we've integrated TLS, we've covered that. We have fewer round trips, so this is going to give us a lower attack surface. Most of our headers are going to be encrypted. We have compulsory encryption because we've integrated the TLS protocol. So there's no clear text transmissions at all. And we've also achieved forward secrecy. So the idea here is that every session is going to produce distinct keys. So if we have a current session's keys compromised, that does not mean that we have keys for previous sessions compromised. Now, a typical handshake with packets and frames included is here. So we have the client on the left and the server on the right. The client sends an initial packet, and within that we have a crypto frame, and within that frame we have a client hello. This is where we're negotiating our cryptographic parameters and exchanging keys. The server responds with an initial packet that's also got a crypto frame in it, and this has the server hello. Now we also have a handshake packet, and in that's another crypto packet, and here you can see that we're getting a certificate. This certificate is going to have the public key for the server, and the client is going to use that to encrypt the traffic. So moving forward there, you can see we've sent our handshake, and this has a fin. So we're finishing the handshake now here, and then following that we finished it, and we were able to transmit our data. Moving on from there. For key cryptographic mechanisms, we have the elliptic curve Diffie-Hellman for key exchange and forward secrecy. We have packet protection via keys derived from the TLS handshake. This is using authenticated encryption with associated data. And the idea here is that each encryption layer has separate secret values for protection of packets traveling in both directions, which is good because streams can be bidirectional or unidirectional, and they can be initiated by either the server or the client. We have traffic secrets derived from TLS and used on all layers, barring only the initial encryption level. This is computer-based on the client's initial destination connection ID. Security threats and mitigation. All of the threats that are sort of applicable to TLS are going to be applicable to QUIC. Perhaps the most interesting is the packet reflection attack, where an attacker is going to spoof a victim's IP address and then repeatedly initiate handshakes with the server. And then the server is going to respond to those handshakes by forwarding the traffic to the victim. And this is going to result in a large number of traffic heading towards a victim. So this is essentially a denial of service attack. Mitigation mechanisms are listed here. We have address validation tokens, stateless retry, anti-replay protection for our zero round trips, and padding and encryption. In terms of scalability, QUIC is very receptive to scaling. We know that its strengths include user space implementation, so it's not in the kernel. We don't need operating system updates when we make changes to it. We have reduced connections via multiplexing, and we have improved throughput due to reduced latency, and connection migration. That's it for the slides. So I'll move on to a capture analysis from Wireshark. Just to cover this first, I decided to go to Google Drive and capture that. I did not clear my cache before I did this, which is a little bit of an issue here because I was already using QUIC protocols on other network connections that I've made in the background without even knowing it. So when I'm going to assess mine here, you can see initially we're sending a 0 RTT packet. That's a little bit different to the diagram that I covered a few slides ago. It's not the end of the world though. An example of a previous connection here, if we look at this very first frame here, we can see a connection number 0. And then when we come down here, we have a connection number of 1. Now, because all of this is encrypted, it's rather difficult to track. So I went and I got the IPv6 address of Google Drive, which we can verify that domain. No worries. Now I have my own here. We're using the temporary IPv6 address there. And then I've also checked for our previous connection, some IPv6 addresses there. Anyway, moving on here. So this is our initial one. So it's a little bit confusing to sort of look at for me, at least anyway. So we have that initial packet being sent there with crypto frames inside. It says we got 2 crypto frames inside. So this is likely going to be, because this is a 0 round trip, we're likely sending previous session IDs, like, we had our security key exchange and negotiated parameters earlier. So this is likely what we're sending back to the server now. And we'll do 2 of those. And then moving on from there, we have our 0 round trip. And I'm assuming that this is going to be our initial HTTP GET request to Google Drive, or HTTPS, sorry, to Google Drive. That's going to be our request there. Now, one thing I will note actually is a packet number. If we come up here to our very first one, we'll be able to see a packet number of 29. So this means we're going to be sending 29 packets from the client to the server. So when the server eventually responds down here, we will find an acknowledgement called largest acknowledged. So there's 2 types of sort of concepts that we should be familiar with. Now, one is just the acknowledgement. So the largest acknowledgement here is saying you send 29 frames, we're acknowledging 29, so they've all come through. We also have ACK ranges. Now, in the event that we might have lost one, we would be able to specify, hey, you sent 5 frames, we lost the 3rd one, so we've received packets 1 through 2 and then 4 through 5, but we're missing the 3rd one, and then the client can retransmit from there. Now, this is the server's response here, and it's broken up quite a bit. I'm not too sure what all they are because it's encrypted and I can't really get much information on it, but my initial thoughts are that it's going to be verifying the previous connection's credentials, and then once it's good, it can send back some cryptographic information or renegotiate the parameters of this connection itself. We'll come down, eventually we'll see a handshake from the client. So this is our client sending the final handshake, and then moving on from there, you can see protected payload. So this is the frame that we've captured that is the end of the handshake, and then from there, it's all of our encrypted data. Thank you.